Okay, so good morning. I'm going to be talking today about a subject which has come in on a number of occasions to our discussions, most recently in the discussion of diagrams last time. And I felt that while I have spoken about it explicitly at times, that I haven't really done it justice. And it serves at once at the nexus of multiple topics. The Oneida lemma, for example, which we want to talk about in some depth, in terms of the treatment of diagrams, in terms of the operation of algebraic ABMs and pattern finding there. And it comes up in many contexts of discussion of Kaprizhev's, these mappings from schema categories to set, for example, because all such polynomial such Cauchys are actually can be decomposed into sums, coproducts of representable functors, excuse me, colimits of representable functors, with poly being coproducts of representable functors. So there's many reasons we want to have clarity about representable functors. And while I've spoken about it some, I haven't really handled it at the level that I think it merits. And I'm hoping to do that today. So previously we've talked about profunctors, and profunctors indeed are yet another topic that articulates with this, and one to which we'll be coming back repeatedly during this presentation, because we'll be dealing with the identity profunctor and the category of profunctors, which is the Hom functor. And the Hom profunctor. But more broadly, we're going to be talking about representable functors as themselves Kaprizhev's maps from what for us will commonly be a schema category into set, which are either directly characterized by their ability to be described by one particular piece of data. Knowing a particular object in C, A, tells us everything we need to know about this functor from C to set. So just that one piece of information, which object you're talking about, will let you follow through and have an entire functor as specified by it. At a technical level, they're either these directly or other Kaprizhev's that exhibits isomorphisms for them, which are basically the same thing except for renaming. And one of the things to which we'll come back, because these are C sets, it's important to be able to shift in this context between viewing them as functors on the one hand, either through a collage perspective or think of them as mapping from C to set, on the one hand, and thinking about them as themselves objects described by or constructs described by those functors, that is, instances of a schema. So, for example, if C is itself the schema of graphs, then the representable functors for that schema are themselves graphs. If C is the schema for causal loop diagrams, the representable functors for it will be causal loop diagrams, can be thought of as causal loop diagrams. They're maps from C to set. If we're dealing with the schema of stock flow diagrams, the representable functors will be stock and flow diagrams. But they're special stock flow diagrams, or special causal loop diagrams, or special graphs. They're the natural building blocks of other such components. Any, for example, causal loop diagram can be composed as a colimit, gluing together these representables for the schema of closed loop diagrams. Any stock flow diagram can be composed out of a colimit, that is a gluing together at certain pieces of the representables for the scheme of stock flow diagrams. So they're kind of these natural building blocks, and they make sense as such. Out of which we build any code sheet for any stock flow diagram, causal loop diagram, graph, etc. It turns out that in practical programming tasks, and amongst other things, in fast homomorphism search, fast searching for these pattern matches, they play a really important role. And on the functional programming side, they play some really interesting roles as well. And finally, the UNA dilemma will be related to these. So I'm going to go back to the discussion of profunctors, because fairly recently we've had discussion of profunctors, and I think people built up some intuition for them. Remember, we described a profunctor in several different ways. One way was a way of thinking about turning A's into B's, or getting to B from A. And we observed that this is a set. For most of the cases we're interested in, for most common cases of profunctors, this is going to be some set of ways, for example, of going from A to B. It gets more complicated if we're dealing with V-enriched profunctors and so on. But for most of our cases, there'll be ways of going from A to B, or ways of making a B from an A. And profunctors provide us a way of turning a way of getting from A to B into a way of getting from A prime to B prime, where A prime is upstream of A, you get to A from A prime, and we get to B prime from a B downstream. So if we know of ways of getting from, from North Station to Central Square, and I know how to get to Central Square from MIT, then I have, from Central Square to MIT, then I have a way from going from North Station to MIT by post-composing with this way of getting from Central Square to MIT. Or equally, if I know how to get to North Station from Rockport via commuter rail, then I have a way of going from Rockport to MIT, taking commuter rail to North Station, going from North Station to to Central Square, and going from Central Square, for example, to MIT. Rockport was upstream of A. We got to A, North Station, from Rockport. And B prime, MIT, was downstream of B. We got to MIT from Central Square. And in general, this maps a way of getting to B from A into a way of getting from A prime to B prime. We can lift it with respect to a mapping for programming. This would be a function for functional programming, a function F going from A prime to A, Rockport to North Station, and another one going, so that's contravariant, A prime to A. And even though here it's A to A prime, G is covariant. We have a way of going from B to B prime. We have a way of going from Central Square to MIT. And we can lift this F and G to get a way of going from F of AB, so the profunctor for making B's out of A's, to profunctor for making B primes out of A primes. So we talked about this before. We had these nice collages to show it. What we're going to be talking about here is actually a specialization of it. You could think of it as a specialization. We're going to zero in this construct of a Hom functor. Okay, and here we're going to be focused specifically on how that snuck through. This should be A prime, A, not A prime here in this. Our focus is going to be on where we have a fixed A here. So we have a way of getting to B from A. And we want a way of getting to B prime from A. Okay. So we're going to have A fixed. Okay. And our interest is in mapping now f of AB to f of A comma B prime. So we're dealing with just one covariant argument here, G, instead of these two here. Okay. And we're going to be dealing with this sort of post-pending, this sort of post-composition. We're dealing with just a single degree of freedom here. A is going to be fixed throughout. Okay, so I'd like to talk about it. There's actually a dual result where A is in the other argument. We're going to focus today where A is in this negative position, is in this position here. And we're going to talk about a Hom function. So many times in our interactions, we've written, Hom, say Hom A comma B. Or equally, if we have a category named C of A comma B, right? And that gives us the Hom set. And you may not have thought of it as a profunctor before, but it is a profunctor. And it's a particularly interesting profunctor. But what's important is that we're going to be dealing with it such that A is fixed here. And we're going to be considering kind of the view of things from A. So how do we get to different things from A, as it were? Okay, different objects. And then we're going to see how it lifts morphisms, kind of along these lines. But let's first deal with objects. Okay, so this is going to be a functor. A is fixed; it's not changing. And this is a functor, so it's going to map objects to objects in C to objects in set. What are objects in set? Someone tell me. What's an object in set? It's a set. Good. Yeah. So it's going to be Hom sets. You're absolutely right, Mehdi, right now. So every object, this is a functor, so it's going to map every object in C, every successive object when we plug it in here, to an object in set, which is a set. Okay. And so, for example, B here is going to turn into some set. So B is going to map over into set, and it's going to be a set, right? This is a C set, right? B, every object here is going to turn into a set. Every object, C is going to turn into a set. And I should have put curly brackets around here, but that's also a set, i.e. A. Okay. I should have nice curly brackets around that, and I stand to be corrected. Okay, so every object here is mapped to a set. It's a C set. This functor maps the objects to sets. But functors don't only map objects to objects. They map morphisms to morphisms. Morphisms here are labeled, and they're going to be mapped to morphisms here. And when we using the same basic pictures here, I'm just restating this in a way that maybe the graphical context is clearer. If we lift morphism F from C, if we plug it in here, right, we get CAF. I know we don't normally write that. Most commonly when we write Hom sets, we write A comma B or A comma C or something. But here we're thinking of it as a profunctor, just a restricted one or as a functor where we only have plugged in this. So it's a functor. It lifts F to CAF. And what does F do? Well, it translates. F goes from B to C. What does CAF do? F over in C goes from B to C, right? Object B to object C. F over in category C. What does CAF goes? Well, it goes from CAB, map of this, of its source, to the map of its destination, CAC. And how does it go? Well, it translates each of these ways of getting to B from A into a way of getting to C from A. Nope. That A is fixed here, right? You can think of this as Bartosz Milewski, compellingly says, as the view of B from A. And this CAF is a way of translating views of B from A into views of C from A. If we know what B looks like from A, and we know how to go from B to C, then we can know what C looks like from A. How do we do that? How do we translate a way of going from A to B into a way of going from A to C? Well, it's the same basic scheme here. It's post-pending. It's post-composition. So if we have a way from going to A to B, these are them. You'll notice where those came from. Think about it for a minute. Where did these come from? Well, I'll give you a hint. J, H, G are morphisms. They are the ways of going from A to B, right? That's what CAB means. It's the ways of going from A to B, which here are just listed out, J, H, G, just right there, right? It's the set of ways of going from A to B. Here, we're going to map each of those ways into a way of going from A to C. How? Well, we're going to post-compose, post-pend, F to this way. So we have J, we're going to have F after J, right? If we can go CAJ here, we can go via this route, the lifting of AJ, then we can always put F after it, compose it, and go to, and we're composing it as it is composed over here in C, right? F after J. And we'll get F after J, which is a way of going from A to C. CIF could also take H and turn it to F after H, which is another morphism going from A to C. Remember, in a category, don't forget the basics, in a category, any two morphisms that are end-to-end can be composed. So there is guaranteed to be, as part of the definition of a category, some composition of F after J. And I've shown it there. And we know where it goes. It goes, F and J are end-to-end. So that's going to go from A, the source of J, to C, the target of F, right? So there's guaranteed to have these. They're just F after J, F after H, F after G, and they go from A to C. So you see how this hom functor operates, not only on objects, telling how to go from the designated point A to the object of concern. All the paths to go could be empty of going from A to there, getting from A to there, right? All the morphisms from A to B, all the morphisms from A to C, but how it also provides this way by lifting an argument here, it provides a way of translating ways of if the morphism goes from B to C, ways of translating things, ways of getting from A to B to ways of getting from A to C. Are you feeling comfortable with that?
Yes.
Oh yeah.
Yes.
Okay. Good. And you may wonder, where did these come from? Well, look, I mean, they're post-composing J with a particularly simple X, which is IDA, right? The identity morphism on A, which again, it should have a curly brackets around that, around it. If you post-compose it with J, you get CIJ, right? You get J. And CIH, you get H, and CIJ, and you get the G. So all these it's the same basic picture. They just happen to go from IDA. Okay, I could spend some time convincing you this is a functor, but I think you'd recognize it as a functor. It observes, it honors identity. It maps identity here to identity here. The home set containing only IDA, and it mapped the identity morphism to identity morphism, and it maps composition over here in C into composition over here. Okay, now I want to talk about this in an applied setting. This is really important. We live and breathe in our applications of ACT, of applied category theory, with AC sets, these hatchets, right? Most fundamentally, when there are no attributes, we think of them as a C set, right? For example, to encode directed multigraphs, we use this schema category, right? So we'll call it GR. Goes by different names with different authors. Okay. So here each object is turned into a set, right? I'm not showing a Hom functor right now. I'm just situating you, reminding you, and by extension, anyone viewing online. V maps to a set, right? And each of these morphisms in the schema category is mapped to a function, right? This is the category of sets and functions. So there's a function that goes from the set of edges to the set of vertices that says for each edge, what's its source vertex, right? So it says for edge 1, its source is A. Edge 1, its source is A, right? Edge 3, its source is B, right? Edge 3, its source is B. And same thing for target, right? And we could enumerate this. We know very well how we could list these things out in tabular form like a database, list V's, list E's. But E would have these foreign columns associated with these functions, right? That specify the source of each edge or the target of each edge. Okay, I think this is all very familiar with those in Cephl and perhaps many of those viewing online. But what I want to highlight here, what I really want to emphasize, is the importance of having this ability to shift, to have lateral thinking, to shift to a different perspective on the same problem. Because this is a perfectly valid, perfectly reasonable way to think about this situation, and there's a lot of clarity there. But I think everyone would agree, this same information can be compellingly presented as a graph itself, right? This describes a directed multigraph. And using conventions from graph theory, we could draw that out. The same information is packed into this graph, right? This is just a certain convention for drawing this information. That's really useful, right? Really useful. In fact, it motivates a lot of our needs to represent causal loop diagrams or to represent stock and flow diagrams or whatever. We'd like to draw these things out, right? Or drawing quantities. And what I'm saying is any C set from graph to set can be drawn as a graph. Do you agree with that? Any C set from schema category graph to set could be drawn as a graph, possibly an empty graph for cases where it's empty. Is everyone on board with that? Every valid C set from this schema category can be drawn as a graph.
Yeah.
Okay. Now, this is going to get us closer to the representable functor. But I want to emphasize something. When I said any valid C set, there are some things you might think are a C set, but they just ain't so. They're not actually valid C sets. And I'm going to pose you an example. So suppose we say, I'm going to build a C set to represent the minimal thing for a graph. I'm going to show an edge. So I'm going to have E be a single. Okay. I meant to have just one. Okay, if we have two, fine. I'm saying I'm going to show a minimal thing with two edges between two edges joined up. But if we have if we have an empty set of vertices, is this a valid C set? Is this a legitimate C set? Is this, by extension, can the C set be created even in a CATLAB? Is this a valid C set?
Your means is without vertices?
No.
Okay, and
No,
why
it's
is it
not
not a valid C set? Yes.
because
And it-
we can't define edges without vertices. We should have a source
Good,
and target
good,
vertices.
that's true. And what mathematically just doesn't work? Why is this not a valid C set? Because what? There is no,
It's not representable.
it's not representable. That's true. But I'm asking you to go down one level. What's wrong? What would source have to look like to translate
Target.
this?
The function must have map any elements of a source
And target.
set
Go-
to.
Mhm, mhm.
We must map every member of the set A and B to another.
Exactly. To a particular thing in the target. And here it can't. There's an empty set of vertices. So what I'm saying is, even if you had this just be A, you cannot describe an edge without vertices. This would not be a legitimate function, right? Because functions can't map a non-empty set into an empty set. Do you agree with that? It cannot map a
Yes.
non-empty set into an empty set. It's not a function. A function, by definition, maps every element of its domain, its input, to some element of its codomain, its output, right? And there's no way to do that. A can't go anywhere. B, in this case, can't go anywhere. Even if it were just A, you couldn't map it. Do you agree with that?
Yeah, for
So-
every function, we should have a domain and codomain.
That's right. And
That
if we have a non-empty domain, we must have a non-empty codomain. Do you agree with that? Because we can't
Yes.
map a non-empty set into an empty set. So what I'm saying is, you might think, oh, well, just encode this as a C set, but this is not a C set. And when it came time to define the function, you'd be unable to do that. You'd be unable to say, what edge one's source is. There's no answer. There's no source. So I'm saying we cannot encode an edge without vertices. And this is a useful thing to keep in mind at a practical level when we talk about representables. The minimal unit of representing an edge, if I could pun, is more than just this edge. We cannot have a disembodied edge without vertices. It needs to go along with vertices. So you might think this is the building block of graphs. I'll just stick it together out of dots representing vertices, and these sort of disconnected edges representing edges, and I've got a graph. And the answer is no, you can't. This cannot be a building block. We cannot. This is not a C set. It cannot be represented as a C set. And this starts to point you to some intuition for why these representables are bigger than you might think. Like, you might think, well, I don't need the two vertices for an edge. All I want is the edge. I want the edge as the building block, but you cannot, it is logically impossible to have an edge. This also gets into practical issues with C-set design and with creating instances of C-sets, because you have to be able to rule out, that we cannot have C-sets that have an empty edge. And sometimes that's why we end up putting spans, for example, in our HMA's models for the I in the middle of a rewrite rule, because I'm not connected to any vertex, but that means there can't be a direct function mapping people to vertices, because it would map a person to an empty set, and we can't have that. So we need to have a partial function. Okay, so what is the representable for edge? What's kind of the minimal thing to represent an edge? Well, it looks like this. Okay, here we have our schema category for graphs, right? And it's a C set, right? Each object is mapped to a set. And each morphism is mapped to a function, right? A morphism in set. And I'm telling you that what the hum functor looks like is going to tell us. So this is the hum functor, right? We're going to plug in each object into here, just like we talked about earlier. Each object got plugged in to get CAB, for example, and each object here is going to be plugged in. And we're going to reason about the hum set, the ways of getting in this schema from E to E in this case. And what are the ways of going from E to E here? Anyone? What are the hums from E to E? Okay, maybe people are confused. All we're doing is retracing this example for the schema category for graph. Here, I'm saying this set was the ways of going from A to B, right? And there was one that was ways of going from A to A, and it was the set. I didn't put the darn brackets around it, and maybe that's confusing people, so I'm going to put them here. There we go. You want brackets? There, I'm going to give you brackets. There we go. In fact, I'll put them in red so you can see them nice and bright. Okay, there you go. There be your brackets. Okay. So every object got mapped to a set, which was the ways of getting in this schema category from A to the other object. So this was IDA, right? This was IJH because it was or IHG because those are the ways of getting from A to B. So let's revisit that. What would this be? What are the ways of getting from E to E? Anyone?
Identity.
Yeah. What are the ways in this schema category from getting from E to V?
Target and source.
Target and source, right there. Do you see that? That's the hum set, right? I'm just plugging in here V here, and I'm asking what's the hum set from E to V. Just like you've read hum set notation many, many times, right? Just like we normally write like CAB or CAC or CAA. I'm just writing that with the name of this category, right? CEV, what is that? Well, it's the morphisms from E to V, which are source and target, right? Are we comfortable with that? That's what that set is. Yeah. And what are these? What is source? Well, what's the function mapped to by source? Well, it has to translate ways of getting from E to E to ways of getting from E to V, right? And what is it? Well, it takes each of these and it post-composes source to it. So it takes this and it takes the composition of this thing with source, which in this case is just source. And the same thing with this and target, right? You remember that rule, right? It was how we post-composed with anything. And I argued this was exactly post-composing J with IDA. That's why this was J. This was post-composing H with IDA, which is H. And here all we're doing is we're mapping each of these into each of these by post-composing with F. We're turning ways of getting from A to B into ways of getting from A to C, right? So that's exactly what this is doing. It's turning ways from getting from E to E into ways of getting from E to V by composing source on the one hand or target at the other. Are you comfortable with that? And are you comfortable with this sort of notion of this is maps to, right? Any morphism here, any object of this, any element of this set is, we just take it, IDE, and we post-compose source with it to get the element of this set. So source with IDE is source. Are you comfortable with this?
Yes.
Okay. Yes.
So then the question is, what is this graph? This is a graph. This is the lateral thinking shift I'm talking about. This is a C set. This is a map. This is a graph set, right? It's a mapping from this schema category to a set. And what I'm saying is any such mapping, you said it earlier, is a graph. What graph is this? What does this graph look like? How many edges does it have? You tell me from reading this. How many edges does it have?
2.
2 edges?
1 edges for
One edge.
edge.
1 edges, yeah.
Okay. And how many vertices does it have?
2.
2.
Source.
Yeah, we'll call them source and target. We'll call this source, that target, and our edge. Well, if we track this here, our edge will its source will be source, and its target will be target. It'll be going from this single, excuse me, this one to this one. Okay. So here, we are going to have this graph associated with this being this graph here, this here graph. This is what this is as a graph. Okay. 1 edge, 2 vertices, and you can trace them through, but the source of the edge for E, 1 edge here is source. That's this vertex. It's called source. This vertex we'll call target. The target of it is target. There we go. So do you agree that this describes a graph?
Yeah.
It's a C set. Describes a graph.
It said,
Describes a graph. Yeah. So this is the function for source. This is the function here for target. Okay. Now I'm going to ask you, and then we'll peek at it. What is the hum functor? If I plugged in, instead of doing it, everything, how to get to from E, instead of saying the view on each other object from E, I asked, how about if we had H sub V, the hum functor H sub V? So this is V, and we could plug in. What would the set of edges be for V? So we're considering we have V here, considering this fixed V, and we plug in anything. If I consider, well, maybe we'll start with the easy one. If I consider VV, what are the ways of going from vertex object in the schema category from V to V? How many ways are there? Right? How many morphism? Just a single one. Okay. So that means
we have 1 edge.
Yeah. Well, okay. So this means the graph that will correspond to this has how many vertices? It will have, so Mehdi just said, and maybe Nona too, this V, if I have V comma V, how many morphisms are in that? Just said
1.
1.
And so that means the graph will have how many vertices?
1.
Remember, it's a C set. V will be mapped to a set with one thing in it. So that means this C set encodes a
Not
graph,
just
which is
identity.
one vertex. How many edges will it have? If I had V here and I considered the map, the morphisms in this schema category from V to E, how many ways are there of going from V to E? How many morphisms from V to E?
0. Empty.
0. So how many edges will we have?
1.
How many edges will we have if this is V?
0.
0.
0.
Zero.
So what will this graph look like?
Vertices is
Yeah,
zero.
what would the graph, if we consider H sub V, and this is V, what will that be as a graph? What will it look like?
Just
Representable.
one dot.
It's just a
Just
single
one
dot. Yes, it's a representable for vertex, which is a single, it's a graph that consists of one vertex. You got it? You got
Yeah.
it? This is just spelling it out, right? So VV goes to this, right? That's the hom from V to V and in the schema category, IDV. So there's one vertex. This encodes a graph. There's one vertex, V maps to a set of size 1, so this is one vertex. E maps to a set of size 0. So how many edges are there?
Nothing.
0. So this is
Nothing.
the graph. So this is our building block of graphs. This and this. Do you get that? This is how you
Yeah.
build up a
Yes.
graph. And remember, we can't have a disconnected edge. So we need our edge to have vertices. More than that, they're actually different vertices in general. So this is our building block for edges. It's not just an edge, disconnected, disembodied edge. It can't be. That wouldn't be a function. It's one of these. So this is a representable for edge, and this is the representable for vertex. Are we comfortable with this?
Yes.
Yeah.
Okay.
Thank you.
Remember, this is a C set, right? By the way, this is a vacuous function. You can have a function that maps from an empty set into anything else. It's just there's only into any other set. There's only one, it's vacuously exists. It doesn't have to specify anything. There's no information conveyed by it because there's no work to do. But it's perfectly valid as a vacuous function. In contrast, this is mapping to an empty set from a non-empty set is not a function. This is a perfectly valid function. It's just a kind of boring one. It doesn't have any work to do. Although you might say, well, it's kind of interesting in its own strange way. Okay. Now things are going to pick up a bit. Here's our schema for ABM. We're going to have a dog. We're going to have a caregiver. There's a person, and we're going to have a home. Person is going to have a home, and a dog is going to have a home. And there's a caregiver relation between dog and person. Okay, I'm going to ask you, what is the representable for each of these? I'm going to ask you, the hard one. Let me ask you this. Maybe I'll ask an easy one first. What's the representable for home?
Only home.
One dog.
Only home.
Only.
Yeah, only home, right? Because there's no, and Mehdi, how did you know that? Because you can get from home to itself, but you can't get from what? You can't get from home here to person.
To person.
So there's an empty
We
set.
can't do-
There's an empty home set for this, right? We can't get here from that. So this will be empty, right? The set into which this translates, which is the set of ways from going to this, will be empty. Do you get that?
Yeah.
Yes.
And the set of ways going from home to dog, how many ways are there from going home to dog?
0.
Nothing.
Okay, good.
Empty.
Okay, let's build our strength a little bit more. What's the representable for person?
Person and home.
Person and home. Good.
Uh,
First of all, why does it not include dog? So that's absolutely right. But why did it not include dog?
dog
Why isn't
is
there a dog in the representable for person?
There
There's
is
nothing,
nothing from
mostly
person
from
to
person
dog.
to dog.
There's no way of getting from person to dog. Why does it have to include home? Because what?
Because there is a way from person to home.
person to
yeah,
home.
is exactly one way, right? So it's going to have one person and one home. Let me ask you along these lines, could we have a C set, a valid C set, with just one person and no homes in it? Would that be a valid C set?
No, it's not valid.
No, because this would not be.
Cannot go to the empty.
Yeah, exactly. Because this would have to be translated to a function which maps a non-empty set to an empty set, just like here. And that's not a function. That's not a legitimate function. So it would have to include a person and a home, and in fact, it is one of each, person and a home. Now let me ask, what's the representable for dog?
Dog, person, home.
Dog,
person, and home.
Okay, dog, person. Okay, so how many dog? It's the representable for dog. Remember, we had like, okay, this had two vertices, one edge. How many dogs in that representable?
One.
One dog. One way of going from dog to dog in the schema, right?
Yeah.
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 Okay. How many persons would be in that representable for dog? One person. Why is that? Because there is what? Because there is
one way from dog
to
person.
Caregiver to dog.
Good. Okay. How many homes would be in that representable?
One home.
One.
Think hard.
Oh. Dog to home. Person to
So
home.
as stated, do we know it's one? So commonly we say this represents a category freely generated by this presentation. Freely generated.
The composition of caregiver and person home is another one. Another way.
So how many ways are there of getting right now? As stated, I'm not saying what you would want, but two from dog to home. We could go this way or we could go that way.
Or this composition to
that. This is not saying right now that if there's a dog and they have a caregiver, they have to live in the same home. You might want to impose that, but that's not currently imposed. And the category is freely generated. And what that means is if you haven't specified via relation, some constraint of equality between morphisms, person after home is a different morphism from dog home. It'll be a different mapping to home. So you would need two different homes because there are two ways of going from dog to home. They're not guaranteed to be the same. If we imposed and so I've written it out here. There's two ways. There's one way of going from dog to person, and there's one way. The stinking. Okay, let me go get those nice red braces that would. There we go. Okay, let's see if we can get that for our dog. We need it for our dog. Come on. Oh my goodness, that's not what I want. Okay, I'll fix it up later. Okay. Now, if we wanted to ensure the understanding that there's only one that if a person is a caregiver to the dog, that they live in the same home, we would add to our schema something that schemas totally support in CATLAB and beyond, which is a relation. We would say dog home is the same as person home after caregiver, person home post with caregiver, person, going caregiver and then person home would be another way to say it. The composition of these two end-to-end. We would say those are the same, and that would be at a sensible if what we wanted to specify is that, look, if a dog is a caregiver, they've got to live in the same home. The dog's home has to be the same as the person home. And we can specify that. And I've indicated it here with a commuting condition. that this way around is the same as that way. And now, if this were a schema where that was a relation imposed on the schema, that this is a presentation of a category where this is imposed, then how many ways would there be of going from dog to home?
2 ways.
If this is commuting?
Yeah, that way is a composition, and that way dog home.
And what this commuting condition is saying is this way and that way are the same. That's why it's a commuting condition.
Just one way.
Just one way. And so the representable for dog would be what in this case? The representable for dog would be how many dogs?
One dog, one person,
one home.
Yeah, one dog, one person, one home. And if you drew it out in the category of elements, you would have a dog, a person, and they would both have morphism in the category of elements to the same home, right?
Same.
Yeah. So you'll notice that this is sensitive to that. Now we have just one, home in this representable for dog. Okay, now I'm gonna finish with a little bit of a more thought-provoking example, which has more relations in it associated with this presentation. Presentations consist of generators. Here we have objects and morphisms and relations. That's what presentations are in CATLAB and beyond. So here are relations. There's going to be a morphism. This may look at first glance like your normal graph category, but it's something more than that because it has an involution operation. So any edge, we can call involution of that edge and we'll get another edge. What edge would that be? Well, if we have an original edge from A to B and we ask for the involution of that involuted edge will go from B to A. So this is a schema for symmetric graphs where any edge has its symmetric opposite. It's kind of a mirror image. But this has to adhere to some properties associated with that. It will observe some properties, right? If we square this involution with involution, what do you think we get back? If we take an edge and we say from A to B and we take its involution, we get one from what to what? The original edge is from A to B, and we perform its involution, we get an edge from what? The original edge is from A to B. We call its involution. We get an edge from what?
B to
A. B to A. Suppose we were to do its involution again. We were to square the involution, apply it again. What we get A to B.
A to B.
So if you square it, it's the same as the identity. You got that?
Yeah.
Okay.
More than that, if I first take involution, so if I have an edge A to B, the source of that edge is what? If I have an edge A to B, just to spell it out, the source of that edge is what?
A,
and the target is
B.
B. Okay, and now if I ask for its involution, and then I take the source of it, what do I get back?
Source is B and target is A.
Exactly. And so if you think about it, if you take the involution, I take the source, I get what I would have gotten by asking about the target of the original, right? If I have an edge from A to B and I involute it, I have from B to A, and I take the source, I get B. That's the same as the target of the original one from A to B. B. And the same thing is true in the reverse. So these are properties of symmetric graphs. Now, symmetric graphs Now, how many ways are there of getting from I'll start with the easy one. How many ways are there? So if I want to consider the representable for E, that's a C set, right? Each of these objects is representable, and for each object, the contents of that C set consist of the morphisms from E to that object in the schema, a corresponding object in the schema, right? So what is E? What does V go to here? What set? The ways of going from E to V. What are the ways of going from E to V here?
Some target.
Target, source and target.
Okay. So that is true. But someone might say, well, wait a minute. There's three ways. I can go source. I can go target. But I'm going to be clever. I can involute and then take target. And that's another way. But is that true?
It's guaranteed by the composition.
No, there isn't.
That's not true, because if I go involute and target, I get actually source. So it's already in my set. There's only two ways of going here because of the properties, the relations here. And the same thing here from E to E. Well, I should have started with this one because this one's easy. Oh, well, easier. But one way of going from E to E is what? What's the kind of trivial one from going? What's the one that's always guaranteed to exist? From
Identity.
Identity. Yeah. What's another way of going E to E that's explicitly drawn out here?
Involution.
Just envelope of identity.
But someone might say, well, wait a minute. I'm more clever than that. There's also involution squared and involution to the third power, involution to the fourth power. Why aren't they correct in that? Why is this Lewis reasoner distorting it? Why are there not an arbitrary number? They might say there's an arbitrary number. There's involution, yes, but there's involution squared, involution cubed, involution to the fourth. Why is that not change this? What is involution squared? What is involution squared, folks?
The identity.
Identity. It's already there. What is involution cubed? Then.
The identity and then involution.
And then involution, which is just involution.
Yeah.
So no matter how many times you do involution, you get one of these. If it's an even number of times, you get identity. If it's an odd number of times, you get involution. So involution to the n. It's going to be one of those, right? Okay, this is a graph. What graph is it? How many edges does this graph have? E maps to a set. That's how we say how many edges it has, right? How big is the set E maps to? How big is it? How big is this set? It's not a trick question. It's two. So how many edges are there in our graph, or symmetric graph, represented by this? How many edges are there?
Two.
Two edges.
Two edges. Okay. How many vertices are there in the representable for E? There's two edges. In the representable for E, how many vertices are there?
Two vertices.
Two vertices. Two vertices. Let's call them source and target. That should sound a bit familiar. Okay. And then, unfortunately, we're out of time. But if you really think hard about it, you ask, well, what's the source of IDE of this edge, compared to the source of the other edge? If you think hard about it, you'll find one edge goes from source to target, and one edge goes from target to source. In other words, goes from this vertex to that one, which we conveniently label source and target. Which is good, because this is what sort of graph? It's not just any graph. It's a what graph?
Symmetric.
Symmetric graph. That is the representable for E.
Yeah.
Okay. What would the representable for V be? Is it going to be some fancy thing? What's the representable for V look like? How many
Only
vertices
V.
would it have?
Only V.
Only V. Only way of getting from V to V
Yeah.
is V.
V to
You
V.
can't go back and then loop around
we
and
can't.
come back again. No.
Yeah, it's not symmetric.
Okay.
We can't
Only
go
V.
come
How
back.
many E's are there? How many ways of getting from V to E are there?
0.
Zero.
0. We
Okay.
can't go.
Yeah. So what does it look like? What does the representable here for V for symmetric graphs look like? It's just a what?
Just a V.
Just a V.
V.
It's just like this one here.
Yeah.
Just a V. Right?
Yeah.
So you might think, oh, it's going to be fancy dancy. No. It's not fancy dancy. It's pretty basic. Okay. So I'm going to stop now. I have another meeting, but I just want to say, these are the key building blocks of coprecities. These are the pieces we glue together with co-limits. Think like push-outs to glue up like one edge to another. We can glue them around. The target for the first is the glued together with the source in the second. We can glue them like tinker toy pieces into bigger structures, right? We can glue together these edges for symmetric graphs here. We could glue together representations of peoples. And if we had networks, we could glue them together into networks. These are the building blocks, the sensible building blocks out of which we build C-sets. And they are at once C-sets and can be represented in database form, but they are also graphical constructs like graphs that we can depict as such. Like we might choose to depict this in an undirected way because we're guaranteed to have one in each direction. Maybe we just put an arrow without showing directions. We know that it's in both directions. Or we put with arrows on both sides, on both sides of it. We can choose our convention to how to represent this, but the point is these are instances of C-sets. This is the representable for E here is a symmetric graph. The representable for dogs is in fact a instance of a population, a particularly simple population for this ABM. The representable for graphs, either representable are graphs, but they're particularly important graphs. They're particularly key graphs for building things up in sensible ways. I will just note, like in so many constructions in category theory, this has a dual. This has a flip side to it, which deals not with ways of getting from A to each successive thing, not views of other things from A, but ways of getting to A from things, other things, ways of views of A from there, and we're going to translate, CBA into CCA, not by post-composing, but by pre-composing with this. And the arrows here are flipped around. Anyway, hopefully that's useful. And think about representable functors, our friends, the representable functors. Know these friends well, respect them well, learn to be very comfortable with them and facile with them, and you will find they're extremely helpful for understanding a vast array of other features. And we're going to be returning to them in many of these discussions of the Oneida, of these cases of diagrams. It turns out they have double categorical analogs of representables. We're going to be talking about them in the context further of pattern finding and harm finding in ABMs, and they are practical. They're not just beautiful. They're not just the natural building blocks. They're super practical. If you have a complicated pattern, and one of the things that it contains is it's glued together representables, and from the Oneida lemma that your population has no instances of that representable, you don't even need to look. It's not there. And the Oneida lemma gives us a really quick way of doing it, because a map into this, we could just look how many instances are there directly with a data structure. In a C set, C of dog will tell us how many dogs there are in the population. And so before we try to do a hum search into it, we can know how many dogs. If there are no dogs, don't do a hum search from some honking big pattern into it, because we're going to end up disappointed. There's going to be none, because these are the natural building blocks. And with those words, I will stop this discussion. Thank you.